Hi, welcome to Chapter 4 of AP Chem, Reactions in Aqueous Solutions. This is Part 1. We're going to go over 4.1, which are general properties in aqueous solutions and precipitation reactions. So the first thing we need to talk about is what is a solution. So this should be a review back from your honors chem days. A solution is defined as a homogeneous mixture of two or more pure substances. And there's two parts of a solution. There's the solvent, which is present in the greatest amount, and the solute, which is the stuff you're dissolving. When water is the solvent, your solutions are a special type of solution. They're called aqueous solution, aqueous meaning water. So in this example, methanol is the solute, and water is the solvent. So now I'd like you to pause this video and do a little activity. I'd like you to draw two boxes, and in one box I want you to draw what sugar looks like when it's dissolved in water, and in the other box I want you to draw what salt looks like when it's dissolved in water. I want you to label your solute and your solvent in your drawings and tell me how you can tell these two solutions apart. So pause this video right now and start sketching. Okay, welcome back, and let's look at what you sketched. Well, first of all, they're both aqueous solutions because they're dissolved in water, and your salt is an ionic compound, so that will dissociate into its ions. So when you drew your NaCl, which is down here, you should have your ions, your Na pluses and your Cl minuses floating around in water. Now when you drew your sugar, so this one is sugar, the sugar will dissolve, but the elements will not form ions, okay? They will not dissociate. So molecular compounds, they can dissolve with water, but they do not dissociate, which means to rip apart into its ions, okay? All substances that dissolve, the process of the dissolving is called solvation. Here is a better drawing. Over here is your NaCl. And you see what's happening is the water is attacking the sodium chloride crystal. And remember, your H2O molecule is polar. So the oxygen has a partial negative charge and the hydrogen side has a partial positive side. So if you look here, the hydrogen side is surrounding your negative chlorine ion, and over here, the negative side of the water, the oxygen side, is surrounding the positive sodium side. And it will rip apart these ions or dissociate them and carry them away into solution. Over here, your sugar molecules are hydrogen bonded to each other. So when you put them in water, the water will break the hydrogen bonds between individual sugar molecules. So here's one whole sugar molecule, here's another one, here's another one. This is the sugar molecule. So it will dissolve because it breaks the hydrogen bondings, but it will not dissociate into ions. So how do you tell the difference between the two of them? Well, the salt solution here will conduct electricity because it has ions in it, and it's also known as an electrolyte. And the sugar one will not. So what are electrolytes and non-electrolytes? So most of your ionic compounds, or all of your strong electrolytes, will dissociate and form an electrolyte. Okay, your weak electrolytes, there really aren't too many weak electrolytes that are ionic compounds. Now your molecular compounds, some of them are strong electrolytes. And those are your strong acids, which we'll talk about in the next slide. And those will conduct electricity. Those are strong electrolytes. And your weak acids are weak electrolytes. And all your other covalent compounds or molecular compounds are non-electrolytes. So remember, electrolytes have ions in them, so they will conduct electricity. Your non-electrolytes, on the other hand, do not have ions. So they do not conduct electricity. So, how do we determine the difference between a strong electrolyte and a weak electrolyte? Strong electrolytes will dissociate completely. Every compound that you put in water will separate into ions. A weak electrolyte will only partially dissociate. Some of them will separate into ions, but not all. And in a non-electrolyte, none of them will dissociate. They do not dissociate in water. And you see in this diagram here, this light bulb is not lit with just pure water. You add sugar to it or sucrose, it's still not lit, but you add salt to it and it does light up. Because now you have ions which are conducting electricity. So strong and weak electrolytes. So again, a strong electrolyte will dissociate completely. And how do we represent that when we're writing a chemical reaction? An arrow that goes one way. Okay, so this means completely. Okay, now if you have a weak electrolyte, only some of them will dissociate, and some of them will stay whole, and that is shown with this. So this is for partial dissociation. Because the reaction could go in both ways. You could have some dissociating or some coming together and forming the compound. So as I stated, I think 2 slides before, strong electrolytes and strong acids are strong electrolytes. And there are 7 strong acids. Here are your 7 strong acids. And this is one of the few things that you need to memorize. Okay, strong bases also form strong electrolytes. And your strong bases are your group 1 metal hydroxides. And a few of your group 2s, calcium hydroxide, strontium hydroxide, and barium hydroxide. If your ionic compound is soluble, it will form an electrolyte, okay? So how do you know if something is soluble in water or not? Well, because not all ionic compounds will dissolve in water, you have to look at your solubility rules. So this is a list of the rules above, okay? Now there's just a few that, if you remember, will make your life easier going forward. Any compound that is bonded to nitrate is always soluble. Okay? And let's see, is there any other ones listed here? All of your alkali metals, the first column on the periodic table, are always soluble. And anything bonded to NH4, ammonium, is always soluble. So what happens when you do a reaction and you form a compound that is not soluble? So if it's not soluble, you will form either a gas or a precipitate. So the first one we're going to talk about are precipitate reactions. So when you mix 2 solutions, 2 aqueous solutions, you might form a solid. And that solid in this picture here is yellow, but it could be white. Depending on what the solid is, the color might be different, but that is called a precipitate. Okay, so if you look here, the example that they're showing you here is 2 potassium iodide, which is aqueous, plus a lead 2 nitrate, which is aqueous. And that's going to form potassium nitrate. And one of the rules I said you should remember is all nitrates are aqueous plus lead 2 iodide, which is not aqueous, so that forms a solid. And that is your precipitate. That yellow substance there is the lead 2 iodide. In some reactions, you're going to form a compound, and that compound will immediately break apart and form a gas. Okay, so anytime you're doing a double replacement reaction and you form hydrogen sulfide, it will be a gas. It will bubble and kind of have like a rotten egg smell. If you form as a product ammonium hydroxide, that will immediately break apart into ammonia plus water, and ammonia is a gas, so you'll see some bubbling going on. Anytime you form carbonic acid here in aqueous solution, it will break apart into carbon dioxide plus water. And here you have sulfurous acid, so that will break up into sulfur dioxide plus water. So these are important to remember. So when you're given a compound and you're asked, is it soluble in water or not, you could refer to the table in your book, which is right here, or there are many tables you can find out on the web, which is where I found this one here. Or I posted a solubility rules chart for you on Schoology. So the first example here, they say cobalt 2 hydroxide. So if you look here and you find hydroxide, it says it is insoluble unless it's bonded with alkali metals and NH4. And down here, if you find it over here, it says the same thing. So cobalt is not an alkali metal or any of those other three. So this will be insoluble. Barium nitrate, all nitrates are always soluble. If you remember that, you don't even have to look at the table. Ammonium phosphates, all ammoniums are always soluble. Sodium chloride, so you find chloride here. It said it is soluble unless it's bonded with silver, lead, or mercury. So this is sodium, is not one of them, so it is soluble. So what does it mean that it's soluble? If you pour it into water, it will dissolve. Okay, it will dissociate. Insoluble, you'll have it won't dissolve at all. So here are some double replacement reactions, and the question is, which ones will form a precipitate? So let's predict our products and balance our reactions. So here we have sodium nitrate, and what did I tell you about nitrates? Nitrates are always soluble, so that will be AQ plus cobalt 2 hydroxide. And if you look at your solubility table, that is insoluble, so that would be a solid. Now we just need to make sure we balance this. Okay, so this one here forms a precipitate. Let's look at the next one. So we're going to get sodium chromate. And if you look up the rules, you'll find that chromates are soluble with group 1 metals, plus potassium hydroxide. Potassium is a group 1 metal, which are always soluble. And let's balance this. This reaction will not. There are no precipitates. Pen is acting weird. So there are no precipitates in that case. Let's look at the next one. So if you're wondering how I'm doing this double replacement, I'm taking the metal from the first compound and I'm bonding it with the anion of the second compound. So here we have NaNO3, sodium nitrate. Any nitrates are aqueous, plus silver hydroxide. Now this one, no need to balance because everything has a plus or minus 1 charge. And silver hydroxide happens to form a precipitate. So this reaction here forms a precipitate. Our next one, we're going to take cobalt and bond it with chromate. And that forms a solid that precipitates out, plus potassium nitrate. Remember, all nitrates are aqueous, and we need to balance that. So So this one here forms a precipitate. So here we have cobalt. We're going to bond it with nitrate, which it is already. So this reaction, since the anion is the same, we're really not doing anything. Just copy it the way it is. And there is no precipitate there. Okay, our last one, potassium goes with nitrate. By now, hopefully you realize potassium nitrate is aqueous plus silver chromate. Chromate has a charge of 2, so you need to put a 2 on the silver. And then you need to balance this. And silver chromate will form a precipitate. So out of the 6 reactions shown here, only 4 will form a precipitate. So now I'd like you to pause this video and choose one of the precipitate reactions and draw a diagram of what your final mixture looks like. So pause the video and sketch a diagram of what the final reaction looks like. Okay. Hopefully you've sketched it, and I've decided I'm going to sketch this reaction here for you. So in my beaker, after the reaction, if it's aqueous, we can separate it into the ions. So I will have Na plus floating around and NO3 minus floating around. And then at the bottom, I will have a precipitate of silver hydroxide. So that's how you should have sketched that. Okay, let's try to do another example together. So here you have 1 mole of barium chloride and 2 moles of potassium sulfate. They are dissolved in separate solutions. Then the 2 solutions are mixed and a precipitate is formed according to the equation shown below, which is balanced already for you. And they're asking you to draw a representation of what is in the beaker after the 2 solutions are mixed. But make sure you take into account the number of moles of each ions in the solution. Okay? So let's just look at our balanced equation first. In order for this reaction to go, we need 1 mole of barium chloride and 1 mole of potassium sulfate. But in our example, they give us 1 mole of barium chloride, but they give us 2 moles of potassium sulfate. So we're going to have an excess of potassium sulfate. We're going to have more than we need. Okay? Does that make sense to you? So, before we draw what we have in our end beaker, let's just draw what we're starting with. Okay? So, I'm starting with 1 mole of barium chloride, and in order to represent that, here's my beaker with my water. I am going to make things simpler, assume 1 mole is like 1 molecule, just to make it simpler for the drawing purposes. So if that is the case, I will form barium plus 2 ion and 2 chlorine ions. So this is going to be the equivalent of 1 mole for my drawings, okay? And then they are giving me 2 moles of potassium sulfate. So if I have 2 moles of potassium sulfate, that means I have, in this molecule here, I have 2 potassiums. So if I have 2 moles of that, then I need to draw 4 potassium ions. And then just 2 sulfate ions. So this is how I'm going to represent 1 mole of barium chloride and 2 moles of potassium sulfate. Okay? Now, according to this reaction, since there's no coefficients here, they just mean 1, we only need 1 mole of each to make our product. So what will our beaker look like in the end after we mix them together? Well, What's going to precipitate out? Barium sulfate. So let's just kind of draw that on the bottom as a precipitate. It's a solid, so it sinks to the bottom. Since we only have 1 mole of barium chloride, that means that we've used our 1 barium with 1 sulfate. Okay? Everything else from our initial drawings is either part of our potassium chloride or extra that we didn't need. So let's look at what we started with. We had 1 barium, which we took care of, and our precipitate, and 1 sulfate, which we took care of. Anything I didn't cross out is still left floating around. So 4 potassium ions, 2 chlorine ions, and 1 sulfate ion. Okay, and that is what it would look like if you could zoom in and see the inside of your beaker. Okay, here we are modeling. Modeling is a big part of the AP curriculum. So if you're confused with how to do the modeling, please let me know.